Hello everyone, I am Hemant Kushwa and with my classmate Atharva Gaikwad, we are presenting Unit 3 Transaction Management and Control. This topic is a fundamental part of advanced database management systems. Let's dive into it. What is transaction? A transaction in DBMS is a sequence of operations performed as a single unit of work. These operations can be insert, update, delete, or read. Let's take a simple example, transferring 500 from account A to account B. We first read account A's balance, deduct rupees 500, write the new balance, then read account B's balance, add rupees 500, and finally write the new balance of B. All of these steps together make one transaction. If even one fails, the whole operation must be undone to keep the database consistent. Next, asset properties overview. To maintain data reliability, every transaction must satisfy four properties known as ACID. A for atomicity, C for consistency, I for isolation, and D for durability. This ensures the database remains accurate even when multiple users or transactions are working together. Next, atomicity and consistency. Atomicity means all operations of a transaction must be completed. Either all happen or none happen. Let's say the debit succeeds but the credit fail. Then we must roll back the entire transaction to the original state. Consistency ensures that the database stay valid before and after a transaction. For example, the total balance between two accounts must remain constant before and after the transfer. Isolation and durability. Isolation means that no transactions should interfere with another. If two transactions read the same data at the same time, it may lead to incorrect updates. Durability ensures that once a transaction is committed, the data remains safe even if the system crashes afterwards. So once money is transferred, it won't be reversed due to power failure or software crash. Transaction states. Transaction pass through various states during executions. First, active, currently executing. Second, partially committed, almost done. Third, failed due to error. Fourth, aborted, rolled back. Fifth, committed, changes are saved. And last, terminated, finished. Understanding this helps manage how transactions behave in real world systems. Next, DBMS scheduling. When many transactions run at the same time, we need to schedule them properly. A serial schedule. Execute one transaction after another, ensuring safety but slower performance. A non-serial schedule mixes operations from multiple transactions, which improves speed but can create conflicts. So we need mechanism to handle them. So far we were understood what transactions are, their properties and how scheduling works in a DBMS. Now my friend and teammate Atharva Gaikwad will take over and explain the more advanced topics starting with different types of schedules and serializability. Over to you, Atharva.
Thanks, Hemant. Let's now talk about some important schedule types. Strict schedules don't allow any reading or writing on a data item until the transaction that last modified it commits or aborts. Cascade-less schedules avoid reading data from uncommitted transactions. Recoverable schedules ensure that a transaction commits only if the transaction it depends on as committed. Serializability helps us check whether a non-serial schedule behaves like a serial one. There are two types are conflict serializability. uses operations conflict to decide order. View serializability compares how transactions read, write values. This ensures that even if transactions run together, the outcome is correct. Conflict serializability. Conflicting operations happen when two different transactions access the same data item and at least one writes to it. To check conflict serializability, we use a graph. If the graph has no cycle, the schedule is safe and behaves like a serial one. Concurrency control protocols. To avoid issue in concurrent execution, we use control mechanisms. Problems like lost updates, dirty reads, and non-repeatable reads can occur without controls. There are three main techniques are log-based protocols, timestamp-based protocols, validation-based protocols. Log-based protocols. In log-based protocols, we use different logs to manage access. Shared logs allow read-only access. Exclusive logs allow both reading and writing. Two phases, two-phase locking divides the process into phases. Growing, where logs are acquired, shrinking, where logs are released. This prevents conflicts and ensures safety. Recovery techniques. If a system crashes, we must recover the database. Some key techniques include undo, roll back uncommitted changes, redo, replay committed changes, deferred and immediate update, shadow pegging, uh, logging with checkpoints. This helps keep the database reliable. Deadlocks and solutions. A deadlock happens when a transactions are stuck waiting for each other forever. To prevent or resolve these, we use wait die scheme, older waits, younger aborts, wound wait scheme, older forces younger to abort. Wait for graphs helps detect deadlocks and if needed, we can roll back one transaction to resolve the issue. This brings us to the end of our presentation. We have discussed all the key aspects of transaction management in DBMS from ACID properties to recovery and deadlocks. Thank you for watching. We hope this has been informative.